Hi everyone, I'm Yinzhan. In this video, I'm going to talk about optimal bounds for noisy sorting. This is joint work with Yuzhou Gu. Sorting is one of the most fundamental tasks in computer science. Given a list of n elements, sorting asks to output them in increasing order, and we assume that all elements are distinct. We consider comparison-based sorting, in which we have to sort, but we only have access to pairwise comparisons. For comparison-based sorting, it's known that roughly n log n comparisons are sufficient, where all logs in this talk are base 2. For instance, merge sort achieves this bound. Also, it's known that roughly n log n comparisons are necessary because there are n factorial different permutations. So we need log n factorial, which is roughly n log n bits to encode our permutation. And each query only gives 1 bit of information. So we need roughly n log n queries to recover this permutation. We consider a natural variant of comparison-based sorting, which is noisy sorting. In this problem, the returned result of each comparison can be flipped with some fixed probability p, and we consider p to be a constant. The goal is to sort correctly with little or 1 error probability. Naively, we can repeat each query O log n times and take the majority to make each comparison correct with high probability. So if we take any classic comparison-based sorting algorithm and replace each comparison there with O log n such queries, we get a noisy sorting algorithm with O n log square n queries. It's known that O n log n queries are sufficient, and other than our work, the best upper bound is roughly 2 over IP times n log n, where IP is 1 plus p log p plus 1 minus p times log 1 minus p, which is the amount of information each noisy comparison gives. On the lower bound side, the previous best lower bound is roughly 1 over IP times n log n by 1 et al. And as we can see, there's a gap between the upper and lower bound. Our main result is a tight bound up to suborder terms for the number of queries needed for sorting n elements using noisy comparisons. And our bound is roughly 1 over IP plus 1 over 1 minus 2p times log 1 minus p over p times n log n. Let me first give some intuition of our bound. For the 1 over IP term, we can think it as some information bound, because each query gives IP bits of information, and we need n log n bits of information in total to recover permutation. So that means we need roughly 1 over IP times n log n queries in total. For the second part of our bound, we first consider the expected number of queries needed to compare 2 elements with error probability less than delta. For this task, we need to use roughly log 1 over delta over 1 minus 2p times log 1 minus p over p queries. And basically, a Bayesian learner achieves this bound. So if we consider the simpler task of verifying whether a given array is sorted, then we still have to compare all pairs of adjacent elements, and each comparison has to be correct with error probability less than essentially 1 over n. So if we plug in delta to be 1 over n in the above comparison bound, we get that to compare each pair of adjacent elements, we need log n over 1 minus 2p times log 1 minus p over p queries. And because there are n minus 1 pairwise comparison to make, we get the second part of our bound. And we call this bound the verification bound. We also study the highly related noisy binary search problem, in which we are given a sorted array and an element, and we have to find the predecessor of the element in the sorted array with error probability delta that's little o1. As we can see, the previous upper and lower bounds essentially match if 1 over delta is small. However, when 1 over delta is big, there is still a gap between the previous bounds. We show a tight bound for noisy binary search even when 1 over delta is big. So the intuition of our bound is the following. Log n over IP is the information bound because there are n choices for the predecessor of the element, and so we need log n bits to encode the predecessor. So therefore, we need roughly log n over IP queries to cover the predecessor. Also, the second term is the verification bound because even if we are given the position of the element, we still have to compare it with the predecessor and its successor to be confident that the position is correct. And each comparison needs to be correct with error probability roughly delta. And so we have to make two comparisons, and each comparison has error probability roughly delta. We get the second part of our bound. We can use binary search to solve sorting in the following way. So we keep doing binary search n times, and for the ith time, we insert the ith element into the sorted list of the first I-1 elements. And after we do the binary search, we get the sorted order of the first I elements. So at the end, we'll correctly sort all the elements. If each noisy binary search has error probability less than 1 over n by union bound, the overall noisy sorting has error probability less than 1. And this strategy was used by prior works. If we use our bound for noisy binary search, we get that the number of queries needed is 1 over IP plus 2 over 1 minus 2p times log 1 minus p over p times n log n. And if we compare it to our noisy sorting bound, we see that the constant factor for the verification bound on the above method is 2, but for our optimal bound for noisy sorting, it's 1. So this means that the previous strategy by using noisy binary search to solve noisy sorting cannot give the optimal bound. In this talk, I will focus on the algorithm and lower bound for noisy sorting. Let me first describe our noisy sorting algorithm. In the first step of the algorithm, we sample a random subset S of n over log n elements, and then we sort S. Because the size of S is small, we can sort S using all n noisy queries with high probability. For instance, if this is the input, and if we sample S to be 296, this step simply sorts S. Now, for each remaining element, we use noisy binary search with error probability 1 over log n to find its predecessor in S. So this process kind of partitions the remaining elements into some sublists. And the number of queries for this step is the following. There are roughly n remaining elements, and for each remaining element, we will perform noisy binary search, and this is the bound of our noisy binary search. And the first part becomes our information bound, and the second part, because 1 over delta is only log n, and the second part ends up being O(n) log n, which is a suborder term. So as you can see, after this step, we get some sublists, but note that there can be some element that are put into the wrong sublists, such as 5 here. And in expectation, we expect to see roughly n over log n elements that are in the wrong sublist. Okay. The next step is to sort each of the sublists, and to do that, we need a lemma for sorting a few elements. We show that we can sort m elements with error probability delta using noisy comparisons in O m log m plus 1 plus little o1 times m log 1 over delta over 1 minus 2p times log 1 minus p over p queries in expectation. So because we can spend O m log m time, we can afford to sort the array by using noisy binary search with error probability 1 over poly m. And therefore, if delta is at least 1 over poly m, we already solved the problem. So from now on, we can assume delta to be less than 1 over poly m. Then we will use insertion sort, whose pseudocode can be found here. And the benefit of insertion sort is that it only needs m minus 1 plus t comparisons, where p is the number of inversion pairs. If we apply insertion sort after we apply the previous sorting that has error probability 1 over poly m, then the expected number of inversion pairs can also be bounded by 1 over poly m. So we use the insertion sort, but we set error probability of each comparison in the insertion sort to be delta over m squared. So first of all, the overall error probability of the algorithm is the error probability of each comparison times the number of comparisons we need to make in the insertion sort, and this can be bounded by delta as desired. Now we consider the expected number of queries. Here, this term is the expected number of queries we need to compare two elements with error probability delta over m squared. And the first term accounts for the case where all comparisons are correct. Because when all comparisons are correct, insertion sort will make only n-1 plus t comparisons. And if some comparison returns incorrect result, then we can still upper bound the number of comparisons the insertion sort makes by m squared. But because the error probability is upper bound by delta, we can multiply delta to this case. Therefore, and because delta and the expected value of t are both small, we can upper bound this coefficient by m, and then we can further simplify the number of queries as the following, which is the desired upper bound of the lemma. So we use the lemma to sort each sublist with error probability 1 over n. Because the size of S is n over log n, there will be n over log n sublists. And on average, each sublist will have size log n. For simplicity, we just assume the sizes of all sublists are bounded by all of them. So after this step, all the sublists are sorted. And the number of queries is just the number of queries of the lemma applying on each of the sublists. And so the total number of queries is this summation. And the first term, because mi is only log n, its summation becomes n log n, which is a lower order term. And for the second term, the number of queries becomes our replication bound. Finally, we just need to fix elements that are in the wrong sublists. Recall that in expectation, only n over log n elements will be put in the wrong sublists. And so we can find them and use noisy binary search to find their correct location. And because the number of elements is small, the cost of this step will end up being a lower order term. So after this step, the error will be correctly sorted. Okay. And here's the summary of all the steps of our algorithm. And at the end, we get the desired upper bound of our algorithm. Next, I will talk about the intuition of our noisy sorting lower bound. The key step in the lower bound is to define the following problem, which we call group sorting. So in this problem, we imagine that we partition the elements to contiguous groups of size k, where elements are contiguous means that they are contiguous in the sorted order. The group sorting problem asks us to sort, but it does not require us to sort elements inside the same group. And additionally, when comparing two elements in the same group, the returned result will deterministically be some symbol star. So if we compare two elements in the same group, we will know for sure that they are in the same group. And on the other hand, if we compare two elements not in the same group, then we also know for sure that they are not in the same group because the returned result will not be star. Okay, so here is an example input for group sorting, where k is 3. One possible valid output is to sort the whole array. And of course, this is a valid output for group sorting. And we can also just not sort inside each group. And so the second output is also a valid output for group sorting. And of course, there are more valid outputs for this input. We first show a lower bound for group sorting. We show that when k is log n, solving group sorting with error probability little o1 requires essentially n log n over IP queries. And this is essentially the information bound. The number of different configurations of groups is n factorial over k factorial to the power of n over k, because the number of permutations is n factorial, but inside each group of size k, we don't care about the orders of the elements. So we can divide by k factorial to the power of n over k. So the number of bits needed to encode a configuration of groups is log n factorial over k factorial to the power of n over k, and which is roughly n log n minus n over k times k log k. And because k is only log n, this ends up being roughly n log n. And also, we can still show that each comparison, the information each query gives is still essentially IP. So at the end, we know that we need n log n over IP noisy queries. Okay, so how is group sorting related to noisy sorting? To show that, we will use an algorithm A for noisy sorting to solve the group sorting problem. Or more specifically, we will use A to sort a list of elements in the following specified order. If X and Y are not in the same group, then their order is their actual order. If X and Y are in the same group, then their order is actually not defined in the group sorting problem, but will enforce the following order. We will enforce their order to be their order in the input. So if this is the input for the group sorting problem, then this is the output we expect from this reduction. So for instance, here the first group contains numbers 2, 1, 3, and they are in the same order as the input 2, 1, 3. And of course, this will be a valid output for the group sorting problem because the groups are correctly sorted. Okay, so we will keep a data structure to maintain elements in the same group. And essentially, if we have some query that returns that X and Y are in the same group, we'll just imagine we add an edge between X and Y. Then two elements are known to be in the same group if they are connected in this graph. So this data structure can be essentially just a disjoint union data structure that keeps track of which set of elements are in the same connected component. Okay, so now when the algorithm A attempts to make a query, we first check the data structure to see whether X and Y are connected. And if they are not connected, that means they are not known to be in the same group. So we query X and Y. If the returned result is not star, that means X and Y are not in the same group, then we return the queried result back to algorithm A. If the returned result is star, then we simulate a noisy comparison between X and Y, where the actual order is the input order. Because remember, for elements inside the same group, we enforce their order to be the input order. And then we also update the data structure by adding an edge between X and Y. And if X and Y are known to be in the same group, then we only need to simulate a noisy comparison as before, and we don't need to actually make a query. So the number of queries we make will actually be smaller than the number of queries the algorithm A makes in general. So because in the views of A, the results it gets are always noisy comparison results with respect to the specified ordering. And because A is a good algorithm for noisy sorting, so with little O1 error probability, it will produce a valid output for group sorting. Now we consider the number of queries we make to the group sorting problem. Every time A makes a query between two elements not in the same group, we will actually make a group sorting query. So, and we use U not equal to denote this number. And it will also make some queries between elements in the same group. However, because we are maintaining this data structure, and each time we actually make a query that returns that two elements are in the same group, we add an edge to that data structure. And that data structure will always be acyclic. Therefore, the number of queries we make between elements in the same group will be upper bounded by n-1. Therefore, by the lower bound for group sorting, we get that U not equal is at least roughly n log n over IP. Now we have an upper bound. Now we have a lower bound for the number of queries A makes for between elements not in the same group. Now we consider how many queries A has to make for elements in the same group. And this is essentially the idea of the replication bound. And in order to just verify whether an array is sorted, we have to compare each pair of adjacent elements, and each comparison has to be correct with error probability less than 1 over n, essentially. And so inside each group of size k, there are n-1 such pairs of elements we have to compare. So in total, we have to compare n over k times k-1 pairs of elements, and each pair will be in the same group. And for each comparison, we need log n over 1 minus 2p times log 1 minus p over p accuracy expectation. And if we use k to be log n, then we get our verification bound. So by summing over the bounds for U not equal and U equal, we get the desired lower bound for our noisy sorting problem. Finally, I will conclude with some open problems. In this work, we are considering the case where P is a constant, but it will also be interesting to extend our result to non-constant P. The second open problem is about semi-random adversary model. In this model, each query is flipped with probability at most P instead of exactly P. And the open question is whether we can get a tight bound in this setting. And that's all. Thank you.